באמת הקשבתי למצטערת, אני נותנת את זה דברים אחרים. לא בגלל שהם לא מעניינים, דרך אגב, בגלל שאני לא יכולה לתקן, שיש לי מה לבד.
אני גם, תקשיב, יש לי... אני לא עשיתי את הקרוב בלבד שלי מחר. נראה לי מחר. אין, תקשיבי.
נראה לך שלך מה?
טובה? אני אצליח לשבת רק אחד. כן, נראה לי עכשיו עומס וגם אפס. גם, אין, כאילו שישי שבת. אמרתי, אני אנוח, אני אישה, אני לא
תעדכני אותי אם את נשארת או לא, כדי שאני יודע אם אני...
את רוצה גם ללכת?
אני לא רוצה לעבור, בואי, זה יום חום שלי בזבוז זמן להיות פה. שבת על מה לעשות. אבל זה בסדר לא נעים לי.
זהו.
כי תרגול קטן שלי.
אבל מה אני אעשה? כאילו, פריוריטי.
מה אני אגיד?
תקשיבי, אני לא יודעת איך לצאת מהרעיון בדרך בערב.
למה לא? היא באת כמה שעות היה?
היום לא, אבל זה כמו שכשאנחנו היינו לא הביאו בכלל. את מבינה? זה כאילו כזה...
והיא תבוא מתי שבאת, היא לחי.
זה עיר הנפמלי, אמרו שכנס מדי פעם לחודש סימן.
Okay, so the last lecture we had determined what is the eigenvectors and eigenvalues of two important operators, position and momentum. And we have seen that basically, as long as we are dealing with discrete, or in the case of momentum, periodic boundary condition, life is well defined. On the other hand, when we are dealing with continuum, some of the mathematics breaks down and we have to go from the usual orthogonality condition into the Dirac orthogonality condition. Okay, shortly we will see how all of this is connected to the principle, the well-known Heisenberg principle of indeterminism. But before that, we'll go into another operator, and that's the energy operator, which actually we have learned everything that we should know about it, but let's just frame it in a different context. So, this is a well-known Schrödinger equation, and the left hand is the energy operator, and the right hand is the Hamiltonian. So we can choose which operator will we use in order to determine what are the eigenvalues and eigenfunctions of this operator. And for the stationary case, which we have already studied, it would be easier to work with Hamiltonian because we know the explicit time dependence. We have done it previously. Okay, so stationary means we have no explicit dependence on time within the Hamiltonian. We can write down the eigenvalue and eigenfunction equation in the following way. Of course, the solution will depend on our system. But generally speaking, we have a base of eigenvectors of this operator, and we have a base of not a base, our list of eigenvalues of this operator. Again, we'll have here cases where the energy is quantized, meaning that we have a discrete value, and we have a case where the energy is a continuum. Again, with all the same problems which we are familiar with. Actually, we'll study probably in the next lecture in which case we have discrete values of the energy and in which case we have a continuum of energies. Someone can guess?
Free particle have continuum of energy?
Exactly. For a free particle, we have a continuum of energies. For a bounded particle, we have a discrete case. And sometimes within the same system, we can have a region of continuum values and of discrete values. The best example for that is the hydrogen atom, which has solutions which are discrete. If we'll just draw the potential, the Coulomb potential, 1 over r. So as long as the energy is smaller than 0, we have a bunch of discrete values. And once we're above it, we have here a continuum of values. So we're going to draw continuum. Okay, someone with a bit of knowledge in chemistry, how do you call the transition from a state here to a state here? Ionization. Just because if I'm taking an electron from here and it's moving to the continuum, it's effectively a free particle, so it's not there. And the atom is left with one less electron, meaning it has a positive charge. It's an ion. So if I kick out an electron from here to here, I have an ionized atom. Okay, all this is in the future, but that's to give you some motivation. Okay. So as we have learned in one of the previous lectures, if I want to write down the full time-dependent solution of the Schrödinger equation, it would be just okay, and now you can stop me and say, why are you still writing the wave function in the R representation? Why not in P representation? The answer is, if it's more convenient for you, where it will be more convenient, let's say, for a free particle, because then P is conserved, write it down in the P basis. We know how to move from one base to another. But at the moment, I'm writing in general in the R representation. Okay, very well. In general, at any given time, it is not necessarily that my wave function is written as an eigenvector of the energy. It could be a combination of eigenvectors. It depends on my initial conditions. For example, if for a system which is not conserving momentum, I measure the momentum, I'll get some wave function which is not an eigenvalue of the energy. For a free particle, when I measure momentum, I'm also in an eigenvector of the energy basis. But in general, not necessarily. So I'll have left out the minus sign. And what happens when I perform a measurement of energy? what will happen? Come on, that's the basic notion of quantum mechanics. I measured the energy and I got some value E. It will collapse. Get just at this time. The eigenvector of the appropriate measured energy. What is the probability of getting a specific E?
Is it the same E you measured?
Well, the probability of measuring a certain E would be AE squared. Of course, in this specific measurement, I certainly measured an energy, therefore that's the energy. But if I'm asking you prior to the measurement, what is the probability of measuring for this wave function and a specific energy E? Square the amplitude, as usual. Same game that we play again and again and again in quantum mechanics. Okay, now let's assume that someone comes and tells you at time t0 this is a wave function. I don't know from where he got it, but he comes and tells you this is a wave function. How do I know what will be the wave function at time t?
Find the eigenvalues of the energy and then multiply by e to the minus t over h bar.
Yes, but I want to start with a standard way that you're already familiar with, that you're supposed to be well versed with it. We have a Schrödinger equation. It's a differential equation. So I have two different ways of approaching this question. One is solve solve the Schrödinger equation with the initial conditions. Second, which we have now learned, is write down psi of E psi r and t0 as write it down in the basis of the eigen vectors of the energy operator. What am I missing? Come on, I thought that I'm tired today. It seems that you were completely out today. Okay, first of all, I should know what are the eigenvalues and eigenvectors of this Hamiltonian. Doesn't depend on the initial condition. It's something that depends only on the Hamiltonian. Okay, so I need to know the eigenvalues and the eigenvectors of the Hamiltonian. And okay, this will give me these components. I'm missing A of E of T. How do I get that? The usual way, from linear algebra. I perform a scalar multiplication between the eigenvalue and the given wave function, and I have A of E in T. Now life is easy because all I need to do to get it at time T is which I have from here. The phase that is acquired from the development in time between T and T naught. If this wave function was in an eigenvector of E, then I'll have here only one component. The phase is not relevant to anything, and I'll get a stationary answer. If it depends on, if it's not in an eigenvector, it depends on the details, because the summation with phase could change with time. So the only way that the system will show time dependence is if it's not in an eigenvalue of the energy from the beginning. If it is, nothing happens to the wave function. Okay. So now we'll move to something that we already know, but it acquired a special name because it was very surprising in the 20s and 30s as a result of quantum mechanics. Heisenberg wrote his PhD thesis on it, failed his exam because of it. Well, let's tell the story. And got a Nobel Prize. So I wish you all that you fail your PhD exam and get a Nobel Prize on whatever you develop. So basically, we know everything about it because it's just a result of all these principles of quantum mechanics that we have already stated. But the uncertainty principle So it basically tells you that if I have two operators and I measured one of them, I don't necessarily know something about the other. Which we understand now why. Because if it collapses on an eigenvector of one of these operators and it's not the same eigenvector as the other, I'll always have a probability in the other. Therefore, I have uncertainty. Although I measured A, I don't necessarily know something about B. Now to the why he failed his PhD. Basically came and tried to give an example why is there such an uncertainty, and he started to talk about, well, if I have a particle, I shine light on it, so while I'm measuring it, I change its position, and I can't measure without changing its position because I have to hit it with a photon and get back the photon. It's not necessarily nowadays considered as the best explanation. It's just an illustration, but fortunately for him, one of the examinators in this PhD exam was a professor of optics that didn't understand anything about what he's talking about, but he heard, well, you have light and you're measuring through a microscope some particle. Okay, my dear Heisenberg, explain me what is a chromatic aberration. And Heisenberg didn't know anything about it. So we told him, well, go back, take courses in optics and come back next year to take your examination because we can't give you a PhD in physics when you know no optics. So for any one of you that unfortunately failed an exam, you can feel, or she can feel good about it. Perhaps she has an open somewhere. Anyhow, so basically we have two operators, A and B. And I want to measure either A or B. So since when this principle was developed, the concept of probability distribution wasn't very popular. They used the second moment, variance. So it's described under the language of variances. Could have been described also on the whole probability. But let's say we have, what is the variance of A? Okay, again, we are inheriting here some cumbersome notation. It's usually called, what am I doing here from the point of view of statistics? I'm just averaging over many experiments that I'm performing here. Sometimes it's called basically it's called the mean value or observation. So basically it's the average over many experiments. And if you remember something from your statistic course, which is questionable, but anyway, does that raise questions or is it familiar? Yes, no? Well, I'm always subtracting the average to find the variance around the average. That's all it tells me. Okay, let's write it down in quantum notation. How do we find averages? The matrix element of the operator. Just a definition. Why am I allowed to do that? Because for any general operator, I should have written here transpose, but I'm talking about physical observables. Therefore, they're Hermitian, therefore, no need to write it. So, can rewrite it in Dirac notation as and the same for B. Now, to the uncertainty principle. There's a lower limit for if I do measurement of A and B, their variance, or square root of the variance in this case, has to be equal or larger than their commutations up to 1/2i. Now, let's stop a minute and think about it. Basically, if they commute, the thing is 0, and it tells me that if I measure A, I can measure B also exactly. We understand exactly why. If it's not equal, we'll have, if they don't commute, then we have to prove what's written here. The second point that it's important to understand is that it's an inequality. I can always find wave functions with different behavior of delta A and delta B. This is a lower limit. Sometimes, like in quantum optics, it's very interesting to put your system in a state that is the absolute minimum. Sometimes it doesn't matter, but however hard you work, if A doesn't commute with B, you have a limit, and you can't
pass this limit.
You can't go lower. You can be higher than that. You could even think about, a lot of work goes in how to approach this limit. You could think also about how to get maximal uncertainty. Well, we'll see an example. Okay. Let's rewrite it a bit. Okay, I'm using what we did 10 minutes ago of writing the operator that operates on the wave function squared. Okay, so I just wrote delta A squared and delta B. Okay, I want to rewrite it. Okay, why is this true? Well,
Yeah.
let's stop a minute and think about two functions.
Yeah.
So I'll write it here. I have two functions, fr and gr. Regular functions. Now, I can write down what do I do here? Take each function that could be negative or positive, square it, meaning it's always positive, and multiply one by the other. Why? Because here, if I have one of the functions is negative and one of the functions is positive, and I sum and then square, I get a smaller number necessarily. It's also known as Schwartz inequality. But
It kind of feels like
It's just like a dot, just like two vector. It will in one side is a dot in one side is a dot b, in the other side is the length of the a and it's square and the other side is the same.
yeah, that's a geometric way to look on it. You can take a very simple. Let's go to the discrete case where it's always easier. Let's have one function that is 1 and 2, and the other function is 2 and minus 1. Okay, if I do the first one, it's 1 squared plus 2 square times 2 square plus 1 square, because minus 1 square is, this comes out 5 times 5, 25. And the other case is 1 times 2 minus 2 times 1, which is 0 squared, and it's 0. And necessarily 25 is larger than 0. And you can, if both of them are positive, it's the same. Okay, so this was an example, not a proof.
Cauchy equation.
Hmm?
Cauchy equation.
Yeah. Okay. If one function is just a scalar multiplied by the other, of course they will be equal. Okay, after this mathematical detour, okay, I want to rewrite what's written here. So, let's make this. Is this correct?
At the end, it kind of feels like triangles and trigo stuff.
No. Has nothing to do with trig. That's no. Why should it be? A and B are two operators, even two Hermitian operators. Their multiplication doesn't necessarily commute, right? So A times B is not equal to B times A. So what's written here is missing something. It's not yet correct. I'll add the missing ingredient.
Isn't it equal to b minus?
So it's equal. This part falls off. So it's
Then you need to do minus there, plus there, no? You have minus half, and yeah, I think it should be plus also. Like,
okay. Why did I write it down in this stupid way, except to torture poor students? Okay, I did it because the upper line is an Hermitian operator. And the lower line is an anti-Hermitian operator. So I'll write it down and show it exactly. So call this operator F. And I'll call this operator and they claim that F and C are both Hermitian. Okay, let's first show that F is Hermitian. Okay, so I just wrote it down explicitly. Nothing more, nothing less. Took everything here and wrote it down. Remember, everything within an average is a number. That's 1.2. Second is basically, not basically, it's by definition, A and B are Hermitian operators. Why are they Hermitian operators? Excuse me? Because our physical operators are representing measurements. Okay, so basically if I go and treat all these 6 terms meaningless to that's what I have to do. Numbers, there's no point to do Hermitian conjugate. Can stop me in a moment and ask why can't it be a complex number? If you ask me, I'll throw you out from the class because we said it several times that a physical observation has to be a number, not a complex number. So I don't need to do anything here, 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 or here. And then I check my memory what is since they're Hermitian, it's BA. And I have proven that this large operator is Hermitian because every one of its terms is Hermitian, and the only thing that happens is this is exchange with the other, but that doesn't matter. The order of addition doesn't matter at all. So F same way exactly I can prove that C is Hermitian. Why is it Hermitian? Because I write here an I. So I'll have to multiply here by minus I in each one of them in order to get C. And this minus I, when I'm doing Hermitian conjugate, will change into I. And exchange the minus plus and everything's good. Do you need to see it step by step? Okay, so F and C are Hermitian operators. Lovely. What else do I know about C? I know another thing about C, which I'll write down here. Here. So all this was F. Because by definition, the commutation relation and that's what I get here, AB and BA with the minus. Okay, so we did here some groundwork to lay a foundation to continue here. Just wrote down explicitly the terms that I had previously. Gave them a short name, F and C. And now, why did I do all this preparation? F and C are Hermitian. What do I know about Hermitian operators?
You can operate them on the other side.
Yes, but what is the result of this thing?
A real number?
A real number is the same here. So we have here two real numbers. Which is exactly the uncertainty principle. So if I want it to be equal, I have to have also f squared is equal to 0. So, after the break, we'll be less abstract and see the canonical example of X and P and see what it actually tells us. But basically, we had two conditions here in order to get an equality. I get an equality when the wave function gives me minimal uncertainty. So if I want to find a wave function with minimal uncertainty, So basically, where lambda is just a scalar, which was in the Schwarz inequality, the condition in order to get an equality, not just an inequality. And the second, what's written exactly here, f should be equal to 0, meaning I'll write explicitly I just wrote into the definition of f explicitly this connection. So here I just wrote the conditions that f will be equal to 0, and into the definition of f I just substituted what's written here. And to rewrite it in a bit more transparent way, okay, so I can rewrite everything as So I have here mathematical conditions on the wave function, which will connect me between the variance in A and variance in B. What does it really mean? If I get a large variance in A, I will have here a small variance in B, and vice versa. Now, I know it all seems very abstract, so after the break, all we'll do is take A and see what it means for these. How to write a wave function with a minimum of uncertainty in X and P. Which we will use all the conditions that appear here. Okay, so let's reconvene, let's say at 3:30.
כאילו, מאיפה מגיע העין?
העין מגיע מזה שזה הדרך היחידה שלך בעצם לוודא שגם אם זה קומפלקסי, יהיה לך משהו אמיתי. כן.
ואז כשאנחנו מדברים אמיתי, זה נטע כאילו להגיד שאנחנו כאילו מדברים על דברים real values, אז
שטיש
בגלל
של
זה זה
טרנספורט.
yeah.
לא, לאו דווקא, את יכולה שיהיה לך עין בתוך
נכון,
זה,
אבל התשובה
אבל
הסופית,
כן, כאילו הערכים עצמאיים הם real value.
אוקיי.
אז פשוט כדי לוודא שזה אמיתי, את צריכה
שנייה, כשאנחנו אומרים על ערכים, כי אנחנו אומרים שבתוך זה אפשר שיהיה משהו imaginary.
נכון.
אז הערכים...
אין בעיה שיהיה בפנים imaginary, צריך שהערכים שאת מאחסנת, צריך שהערכים העצמיים לא יהיו.
שכאילו,
כשאת מאחסנת,
התוצאות.
כשאת מאחסנת מטריצה, נניח פה יש לך i מינוס i 0 0, אז כשאת מאחסנת אותה, הערכים יהיה לך real. אוקיי?
עכשיו הוא התחיל לדבר על כאילו, uncertainty principle, ואנחנו מדברים על כאילו שזה יהיה the minimum, נכון?
כן.
למה זה, I'm just like,
why it's true.
no. Like, if we're talking about the uncertainty principle, why does it matter? Like, what does it matter to us to have the minimum uncertainty?
It's not like you don't want the minimum uncertainty, but in some cases it's more interesting.
What,
Like some cases you start like your minimal is the starting point. כאילו זה הנקודה שממנה אתה יכול כאילו את לא יכולה לרדת ממנה. זה נקודה שממנה זה המינימה, בוא נגיד אם יש לך משבצת, אם העולם הוא משבצות זה המשבצת הכי קטנה. את לא יכולה לרדת יותר קונטיניום, אין לך קונטיניום.
okay.
את לא רוצה שזה יהיה ככה, אבל את רוצה שזה יהיה כאילו, זה כל מה שאחרי זה. כאילו, לדוגמה, אם עושים את זה חיזאית, אז יהיה לך h בחלקי 2. זה אומר הכי קטן שקורה, משהו עושה.
נכון, הוא הולך לעשות כזה, הוא סתם לא הבנתי כאילו, למה זה חשוב ומעניין אותנו שזה יהיה כאילו בסוף, כשאנחנו מדברים על ה-uncertainty בתוך זה תהיה uncertainty. דיברנו על זה כבר, שאם אנחנו עושים measure של משהו אחד,
נכון, אבל פה זה אומר לך כאילו זה הבנדר, זה הכי למעלה.
כן, לא הבנתי, ולמה זה כאילו מה זה משנה?
מה זה משנה? זה משנה שזה אמרתי, כאילו זה הכי קרוב למה שאת יכולה להגיד.
כשאת אומרת את זה, את מתכוונת כאילו הכי מדויק שאפשר.
כאילו, אני מתכוונת שאת לא תקבלי,
if we're saying it's like the minimum, we're also in a way saying like this is the closest to the true answer that we can get for this kind of keep. Because I'm just saying,
that's
like,
uncertainty.
we talked about like if you measure A, you don't necessarily
No.
know anything about B, right? So,
נכון.
שזה נכנס תוך ה-uncertainty. So if I'm measuring A, if I have the maximum uncertainty versus the minimum uncertainty, what does that really help me with? The way I do A and B.
כאילו איך זה עוזר לך ל-IPD?
כן, כאילו, אני יודע מה הוא עושה, אבל לא הבנתי כאילו מה החשיבות. אבל גם, כשהוא אומר אינטגרל, למה הוא מתכוון?
אני מתכוון שיש לך שתי אופציות, כאילו יש לך כמה סוגי בעיות. יש לך בעיות שאת כאילו מתייחסת לעולם, למי שמסביב, כאילו זה גלים. גלים, פשוט גלים. ויש cases, כאילו לדוגמה כשאת בבור פוטנציאל, את לא מתייחסת לזה, אין לך אופציות, אין לך אינסוף אופציות. יש לך רק
מה שבתוך
אופציות
אוקיי.
מסוימות, וזה כאילו מקבונטט, וזה הופך את זה למדי, כאילו את יכולה לספור את זה. פה זה לא, פה יש לך רצף של אפשרויות. הרצף הוא, אין כאילו, בין פה לפה יש גם אופציות, הבנת? פה, במקרה הזה, אין לך אופציות בין לבין.
אז מה זה קונטיניום ומה זה?
אז קונטיניום זה לדוגמה, נניח, חלק חופשי שלנו כיף, אין לו שום אקסטרקשן.
שאנחנו עוברים קונטיניום.
ואז את יכולה
מדברים על
להגיד,
כאילו אינסופי כזה.
אין סופי, הכל טוב לו.
Okay, that makes sense. That's why we take from like the wave and we talk about turn it to a
כן,
project.
כן. עכשיו, כשיש לך את זה, אז את יותר תלכי על מטריצות ועל דברים יותר כאילו כאלה, וכשיש לך יותר את זה, את יותר תלכי על לבד.
כן,
כאילו,
בגלל זה אנחנו
אינטגרלי.
עושים כל ה...
נכון, בגלל זה את עושה גם וגם
שאלה.
יש חשיבות?
העדה שלי, אני יכולה להיות שאני מתחילה לחזור כל החומרים לכל דברים. והסתובבתי שאני לא פעם.
מה?
אבל באמת אני צריכה לבדוק, אני צריכה לבדוק על האינטרציה שלי, תחזיר לי קצת.
איזה מודלים
Okay. So let's look explicitly in the case where we consider two operators, position and momentum. So we have x and p of x. First of all, who said that we can't get a case where we have zero variance in both of them? Well, mathematics tells us, or when we're checking commutation relation. Okay, I just wrote down explicitly the expression for the commutation relation. So the commutation relation between x and p is just I times h bar. So it's not zero, it's a constant. We could go back and, okay, let's see another example. Let's see the commutation relation between x and py. Someone can immediately give the answer.
Should be zero.
This zero because but y doesn't depend on x. Therefore, it's just a constant. Should have said something. Same argument. Just Okay, in general, and it's almost trivial. I cannot measure both x and the momentum in x. I have no problem of measuring the position in x and the momentum in z, or vice versa. So, in the x direction, which is Heisenberg's uncertainty principle. We can't know x and px up to a variance of half h bar. Okay, let's create a wave function for which it's not larger than, but explicitly equal. Okay, I have to define this wave function by something. What could be the something? It could be its initial position, which is a matrix element of x, and its initial momentum, P0, so this is basically notation. So I have one equation this, if you remember, was our first condition in order to get an equality instead of inequality. Just wrote it down explicitly. And we, even using the second condition that the average of f will be equal to 0, we can say something about what is lambda. That was from the condition that the average of f would be equal to 0. So I'm using the two conditions that I had previously, one of them just determining lambda and the other one leaving me with an equation. Okay, I'll write down a solution and show that it's correct, and even explain what is the logic behind this solution. First, let's see if mathematically it's correct. Okay. So let's see what's written here. Okay, first the derivative. Okay, I have a derivative of an exponent, I'll be left with an exponent. You have just to do an internal derivative of what is appearing in the exponent. Okay, so I have from the first term, from the second term, sorry, I forgot the term. Sorry for not rewriting the whole exponent. I just wrote down explicitly the derivative and everything else that is appearing on the left-hand side. You can see that this guy and this guy cancels. exactly what's written here. So it's a solution. Why is this a solution? Let's look first on the x-dependent part, which has no average momentum. Okay, if I write it down in a basis of p instead of writing down in a basis of x, which at the end of the day is just the core principle of uncertainty. I move from one base to another base and ask what happens. How do I move from real space to momentum space representation? We did it in the previous lecture. What is the mathematical operation that I do? Fourier transform, right? What do we know about a Fourier transform? Fourier transform of a Gaussian is another Gaussian. So this is the most, when I'm transforming from one to the other, I don't want to create a whole mess. That's the easiest function to choose. It also comes out to be the function of the minimum uncertainty. Just because you left one form and you return to the same form in the other basis. You left an exponent and you were back to exponent. Now, the second part, okay, let's look on the case where you have no momentum. Okay, P0 is equal on the average. P0 is equal 0. Does it mean that you have no momentum at all?
No average.
You have no average momentum, but you have you could have performing a measurement seeing a momentum. What does it mean that you have no momentum on the average? That this wave packet remains centered around x0. It just becomes wider and wider, but the same way on both sides. So that, and we'll do it explicitly in a future lecture. Why do I have I times P0? We have proven that if I want to have an average momentum, I have to have an imaginary part of the wave function, right? Proved it a few lectures ago. So this is the result is the result of an equation, but that gives us some physical picture about why it looks like an exponent times a phase. Not an exponent, a Gaussian times a phase. Okay, until here about uncertainty. if you remember anything from mechanics, equations of motions and conservation laws are a very important part of mechanics. They're also very important in quantum mechanics. Okay, but the difference is here we will be speaking about observables, average values. So let's say I have some physical observable A. And I want to know how its average develops with time. Okay, so the average value of the observable A depends on the wave function, of course. So I've written it explicitly here, and you can guess why I did this thing. Why? Because that is the operator that appears on the left hand of the Schrödinger equation, which describes the development in time of any wave function. That's why I'm adding this part. But at the moment, I just want to see what is the mathematical structure of this expression. Okay, let's leave Dirac and write it down explicitly. So this is I h bar. Just wrote down explicitly what does it mean, this matrix A. Okay, in principle, this could depend on T, this could depend on T, and this could depend on T. Okay. So I get 3 terms. Now I scratch my head a bit. And remember that I have something that's called the Schrödinger equation that tells us explicitly explicit. And just to remind ourselves, for the millionth time, I'll ask you, why don't I bother to put an adjacent Hermitian conjugate on H?
Because we'll measure it.
Because it has to be Hermitian. Most answers in quantum mechanics is because the operator is Hermitian. Okay, so I have this guy, I copy from here, I get minus IH bar goes before all these three. Why? Come on, I gave you the answer a minute ago. Because it's a mission. And I have here minus HA, and here I have plus AH. What's it called? Accommodation relations. That's why this part comes here after we became expert in commutation relations. So let me rewrite everything that's written here. Lovely. If A doesn't depend explicitly on time, and I want to know if an average of an operator changes with time, all I have to do is a commutation relation between this observable, between this operator and the Hamiltonian. If they commute, the average doesn't change. Again, trivial, because if they commute, they have the same basis. If they have the same basis, and the development in time, in case that A doesn't depend explicitly on T, doesn't change. So if I know what happens to the Hamiltonian, I know what happens to A. End of story. But here is the full mathematical proof. So if someone comes to you and asks you, will this observable on average depend on time? Perform a commutational relation with the Hamiltonian. It's zero. It's conserved. That's a conservation law, because average doesn't change. If it doesn't commute, then it may change with time. Okay, this is the point in the course where we stop to talk about general principles of quantum mechanics and start to solve specific examples. The first very challenging example is a free particle. Why do I call it very challenging? From one point, it's almost trivial. We solved it, we know exactly how the solution to the Schrödinger equation looks like. We know everything about a free particle. On the other hand, it makes no sense. And I'll try to explain it in a moment. Okay, when we approach a specific problem in quantum mechanics, usually what is the first step? Writing down the Hamiltonian, the classical Hamiltonian. Because then we'll know what are the operators that exist for this Hamiltonian. We know what are the functions and eigenvalues of this operator. We can proceed. So, classically, a free particle, let's write it down in one dimension just for simplicity. This is Hamiltonian. I hope it's no great surprise for anyone. Now I can sit down and write the solution of this of the equation. But there's no point. Because I know exactly that Px commutes with H. Right? So the bases of Px are also the bases of H. And since we did already calculate the eigenvectors of Px, I know also the eigenvectors of H. So this is the basis of H. Now, the eigenvalues are not the same. Remember what we said, that two operators may commute, but give us different eigenvalues. They give us necessarily the same eigenvectors, but not the same eigenvalues. And the reason is very simple. Here is Px squared divided by this guy. So the eigenvalues are e to the I kx. Okay, and the corresponding eigenvalue could write of P, but it's customary to write it as E of K. Remember the relation H bar K is P. Pay attention that while Px could be any value between minus infinity and plus infinity, energy is always between 0 and infinity, because it's squared. Okay. So why I said it's, and we can write it down the other way around. K is equal square root of 2me K divided by H bar. So we have the eigenvalues of the Hamiltonian, but these can't be the wave function of a free particle. Why?
Because it's square and it grows in the whole space is infinite.
Exactly. It's not normalizable. So, what is the meaning of this thing?
It can combine a lot of kind of K and then so we can get a normalizable wave function.
Exactly. Basically, we cannot get in nature an electron which is in a free electron which is in a pure value of K. Actually, those of you which have some experience in optics, it's the same case that you can't get a photon or a packet of light that will be a pure photon with a definite frequency. You always have some spread of frequencies. You have to create a wave packet. Any electron or photon in nature won't be in a specific value of P or K. It will be a wave packet. Okay, because a pure photon basically should be spread out over the whole universe. You never have that situation. Well, another way around it is our periodic boundary condition. If I can limit my electron to live on a ring, for example, no problem. I can have the electron or the photon being in a pure value of P or frequency. So how do I create a wave packet? No problem. As usual, I gather a lot of Ks, give each of them some weight, and then I get a wave packet. Or explicitly, for a free particle, a wave packet which is simply saying put a weight here, write it down as the eigenvectors of K, put in the time development, and you have the wave function at any given time. How do I find AK0? We did it an hour ago. Which is also known in some authors as a Fourier transform. It's nothing special about the Fourier transform, it's something special about the basis of the momentum. So that's it. Give me the wave function. Oh, okay, at 0. Give me the wave function at 0. I'll build the Fourier. I'll build the amplitudes, stick it here, and I have the solution of the wave packet at any time. You see a very similar construction to what we did for the minimal uncertainty wave function. So let's go back to that and start from a wave packet that's a Gaussian. Let's prove what I said, that a transform over Gaussian is a Gaussian. So this is a typical Gaussian with a width delta 0, and the only thing I have to worry about is normalization. So we'll go back to what we know about integrals of Gaussians and find out that the normalization in this case would be quarter. Okay, because one thing I can tell you, okay, look at, it's a definite integral between minus infinity and infinity, and this you can check up in any table of integration or nowadays in any mathematical app or anything. But I want to show you a nice trick which makes life easy, how to solve these integrations. You probably have seen it, but just as a reminder, just since Gaussian integrals will come again and again and again in this course, for example, in the case of harmonic potential, so I'll do it once. Okay, let's say I have an integral dx because that's my integral. Now let's that's my integral. So in one of the rare cases in mathematics, I will make my life simple by making the question more difficult. So I don't want to know what's I want to know what's I squared. I'm just writing x and y, so I know that it's different integration variables. Okay, so I didn't know to solve the integral on x. Now I'm asking the integral, the two-dimensional integral. Okay, let me rewrite it. let me use the following placement, or moving in 2 dimension to polar coordinates. Okay. So I can rewrite what's written here as the usual transformation to polar coordinates. Okay. This is easy. Has no dependence on d theta anywhere. And okay, let's do another step. Okay, let me do the following transformation. U is equal okay, just placing squared, of course. So far, so good. Hopefully. This is a lovely integral because it's equal 1. Don't believe me, perform it and convince yourself. Yes, and now I should remind myself I'm not interested in I squared. I'm interested in I. Square root. Okay. So if I'm taking psi square and performing the integral, you can substitute and find that the normalization is what appears here. Perhaps I should use here a instead of that, not to, because when you are taking squared, what happens instead of 4, you have 2 here. Okay, so this is our wave packet, and in the next lecture we'll see how it develops in time. Okay, and from now on I'll just write down the result of any Gaussian integral because you know how to perform it. And it's a neat trick. And as I said, one of the only examples that I'm aware of that by making the problem more difficult, it became solvable. Okay, so see you next week. Just not to because this is not the integral that we perform. We perform actually the normalization equal 1 is psi squared.
Right.
So that's actually minus x squared over 2 delta. Because squared of x is twice this guy, so this is the integral you want to perform, so you will end up here with 2 pi delta 0.
Instead of 4 pi.
Yeah.
Oh, because then you go back to this and then it's squared. Okay, got
But
it.
then you get here the 2.
Yeah.
So,
Okay. Also, before we went into this, you went over the principle and you talked about the minimum where you were sort of looking at. I was trying to understand, like, what's the importance of looking or trying to get the minimum uncertainty?
okay, one is just amusement.
Okay.
Just what is a wave function that will give me minimal uncertainty? But then it comes to very practical use when you're considering the case, let's say in optics or photon, which is the same game. You want to have pulse. Now you have 2 things about the pulse. You have time and frequency. Sometimes you measure time, sometimes you measure frequency, and you want that you'll get if you measure both to get minimum uncertainty. You want a pulse that has some finite width, but will give you also minimum uncertainty on measuring the frequency.
Okay, so what we're saying when we're talking about the minimum uncertainty, we're trying to say that we're looking for the closest possible real answer.
Right.
Okay.
If we measure one or the other, we have the less uncertainty about the second variable.
Okay.
You want to know when the pulse arrived, but also what was the frequency of this pulse.
Got it. And so,
Because let's say in optical fibers, you want to transmit data that first of all, you know what is the frequency because you use many frequencies on the same line, so you want to be able to separate between them, and you want to get your bit, your 0 or 1, did I have a pulse there or not, within some finite time.
right.
So how to minimize the uncertainty in both of them? Use Gaussian pulses.
Got it. then again, just like understanding, so the uncertainty is also related to having the same, like, if they don't have the same bases, we're talking about we can't, once we measure A, we don't know what's happening B, so we then look at the uncertainty principle.
Right, in order to say how much did it spread in the other.
Okay. To give us some sort of like possible image of what is happening.
Right.
Okay. Thank you.
כן עם כוכבית.
אוקיי.
זאת אומרת שאני לא נוטה להידבק לצורה מסוימת של מבחן. זאת אומרת, אני אעלה והכל טוב, אבל כהכנה למבחן יותר טוב לעבור על החומר וקצת לתרגם מבחנים, ולא הפרקטיקה ההפוכה של לטחון מבחנים ולהתעלם מהחומר הנלמד, ואז פתאום אני משנה קצת את הצורה. זה לא בגרות שיש שם 5 שאלות שחוזרות על עצמן.
אוקיי, תודה.
רק ניחוש, וגם יותר מזה אני מנחש בשיעורים הבאים נלמד את זה, אבל אם הגאוסיאן ב-X עובר להיות גאוסיאן גם כאילו התנא והמיקום הם שווי ערך במונח הזה של הגאוסיאנים, אז ההמילטוניאן יצטרך להיות T בריבוע כפול משהו ועוד X בריבוע כפול משהו?
שזה נקרא פוטנציאל הרמוני. ולכן אמרתי שהצורה הזאת של הפתרון תחזור אלינו.
אז כאילו רק מתוך ההיגיון של הם אמורים להיות שווי ערך.
נכון. אם ההמילטוניאן הוא בי-לינארי, כמו שהם קוראים, לא בי-לינארי, בי-קוודרטי, זאת אומרת x בריבוע ו-p בריבוע מופיעים שם עד כדי קבועים, אז זה כופה עליי צורת פתרון מסוימת.
אוקיי, אז אנחנו בטח
נעשה את זה במפורש, ואני אגיד לך יתרה מזאת, בכל תורת שדות, או שהמבנה הוא כזה ואז יודעים לפתור אותו במדויק, או הוא לא כזה ואז משתמשים בתורת הפרעות, כי אנחנו לא יודעים לפתור.
כמו טיילור, אבל...
טיילור, קירובים. ואם הקירובים הם כאלו שמתנהגים יפה, אנחנו יודעים לקבל פתרונות מעולים כמו ב-QED, ואם זה לא כמו ב-QCD, אז יש לנו צרה צבורה.
אוקיי. טוב, תודה. תודה.